Hi everyone, we are from Commuji company and today we are going to present the product that is an innovation that suggests the right emoji for the right message from your text message. Super. Um, so first I will introduce what is the problem for that inspire us to do this project. And so nowadays we mostly use a text chatting, right? And however, the problem for this is, as we are human, we mostly use emotion to express, so it can make the communication better and easier to trying to communicate. And here's the problem of text chatting here. Even though it has emoji, but you can imagine that when you try to find the right emoji, there has 100 available emoji, so you may be lazy to find. So here, what we decide to do is we try to rather find an emoji for yourself. We will suggest emoji for you for the right message. Okay, and here is how we will present you. So first, I will tell you what is the data that we will use to train our BERT model, and next we will tell you how the model BERT works, and the next one is how we use that data to train the model, and next we will evaluate our model. Okay, and so first of all, data we are use from the Kaggle platform, and then here, the data that we obtain here has T5, training, validation, and tested, so we don't have to split by ourselves. And luckily, there is no missing value found, so we don't have to drop or we don't have to try to do some pre-processing stuff again. Okay, so now let's see what does the data set looks like. Okay, so first of all, as we said before, we try to classify the text message, which is the in column feed text, and emoji is the emoji that we will try to predict. So this is the food that we will try to let bird eating, so it can be Commuji. Okay, and the whole data set, the size for them is 20,000 and two columns. Um, this note that this is the data set that gather both training, validation, and test set together. And the output, you can see that there is a 6 emoji here. That is our 6 level, which include joy, sadness, anger, surprise, fear. Okay. However, you can see that most of machine algorithm cannot learn anything that is not numerical. So we have to convert into in form of label encoding. So we convert into form of this integer. Anger S1, fear S4, and so on. And next, we want to check the size of the training validation test set first. So to make sure that it is balanced and it's fair to use. And then the results show here that the label count of each is proportionally balanced. So it is ready to use. Now, the main part is how this model BERT works. So, first of all, thank you to the hacking platform that provide the P10 BERT model. This platform is really good. They provide a lot of P10 model that based on the transformer and BERT architecture. I really recommend you to explore by yourself. And here is the P10 model I use. It called BERT based on case. And if you want to see more information about that, you can scan that QR code. And then here is what does the architecture is looks like. You may wondering what each each input and what does the function like multi-head attention looks like. That's okay because I will explain later after that in a simple way. Okay, and here is the parameter and summary of the model that how this P10 BERT model train. First of all, they use the loss function as a cost entropy function and activation function as a GLO and optimizer as the RWW. So Yellow is just like the Lilu, but when when the value is negative, it will perform in form of like normal distribution instead of treat it all as zero. But for the adaptable, it simply just update the learning rate for when the when when the epoch is higher and higher, the learning rate will be lower and lower, something like that. It will update gradually. And for how does it different from the Adam? Well, Adam the build here is stand for wear decay, and when the time pass, they will have parameter called weight, and then I'm not going to explain further. And here this model has 12 attention head and 12 attention layer. Unlike the transformer architecture that has only 8 attention head, so it might leave the transformer cannot really learn the to learn something that is more complicated than BERT. Okay, so now let's start our journey. How does this model do it? So first of all, here is one of our observation. Let's say I feel romance too. It is 4 words, right? And when we input it into our model, the model will automatically put CLS as at the front and save at the end. And so it means that the number of token here will be passed through as always. And then once we got this one, we will convert it into input token. So based on the dictionary here, note that the number of total input token is 30,000. What does it mean? So well, the maximum possible input token is 30,000. It cannot be reached more than that. In this case, you can see that CLS input token for CLS is 101 and fill is 1045. And set is 102 and so on. Is really based on a vocabulary. You don't mind why it is not, because it is based on dictionary. And once we got the input token, now we want to do some kind of like input embedding. We will transform it into form of vector, which also use input token as key and then input embedding as well. Note that the size of input embedding for our P10 model here is 768, which is very large. Um, and once we got input embedding, now remember that when we do something like text stuff, we need to really care what does the or which one come first. Like I feel romance and romance feel ice. The contextual meaning should not be the same, right? So here is how BERT preserve the order. They will make the function called position encoding, and then the input for this function will be the position index for each word. In this case, you can see that 0s is the first position index, so it is 0, and I is 1, and fill is 2, and so on. Once we got that, we will plus them together. Bam, just like this one. And note that what makes BERT special here is it allows them to perform it in parallel. You can see that just plug the position, and each word is really independent because yeah, just plug the position index to the position encoding and then just plug together so it can perform in parallel. Okay, next once we got a sorry, the result here is called position embedding, the sum of them. And once we got the position embedding here, we will plug it into this function called 12 head attention. The reason I call 12 head because the BERT based on case had 12 attention head. So so I call it instead of multi head. So and then we will go through the add plus norm, and then we will repeat this for 12 times. Yeah. Okay, but before I tell you what is the 12 head attention, so I would like to introduce that this position embedding will be transformed into QKV respectively, and they are different. You may wondering what is them. Okay, I have analogy for them. Let's think about when you do you searching for the YouTube video. Let's say you want to see what is the k-mean clustering. That is the QD what you really want the YouTube to search for, and key is the result that they suggest. And you know that the thing that they suggest must have the similar to the keyword that what you search, right? So the first video that pop up is just like a key that has the most similar to the keyword, just like that. And here, each key has their own value, but it is hidden now. But once you click to that key, the value will be pop up. Okay, and here, this is how we got QE key value. So simply, they are both the linear transformation of the position embedding, but the linear transformation of them has a different parameter, which got taken by the p10 already p10 them, so we can obtain the right parameter for the linear transformation. And okay, before I want you to know what to do with the query key value, then I want you to see the analogy for the image. This is just like a computer vision. So first of all, the image here is the input for both the QE function, key function, and value function, right? We transform it into QE key value, and then when we QE multiply by key and scale it, we will got a filter, which in this case we can see that filter is it will particularly focus on the character, but not the background. But the value itself is just like it's just the original image, and then we multiply together, we will get a filter image. But note that there are more than one head, right? So what we can do now is we will got the more than one filter image. So you can see that um, so you can see that there are more than one filter image. And if we compare to our case, which is text, you can see that the input for that is the text. In this case, I feel romance too. And then when we go through this attention head, the filter value is just it's just the word, the same word but different weight for each word. What does that mean? Well, for the word I, you can see that they really focus on the word I more than feel and to, and slightly more than romance. So the weight here is converged to 1, while feel and to is converged to 0. So for the and each attention head here is focused on the different word. So when we said attention head one focus on the word I and romance, it doesn't mean that other attention head will focus on I and romance too. They might maybe focus on the free and two and maybe SEP and CLS. Okay, once we got the filter value of all attention head, what we do next is concat them together. So in this case, the size is respect to each attention head has the size 6 and we have 12, so we multiply it together, we will get 72. We stack them together, and then what will we do next is we will try to make the output here has the same size as our word embedding or position embedding, which you can see that it is 768 multiplied by 6. And next, once we got the output, we want to go to the function called add add, right? And it is simple, just add the position embedding plus with the output here again. We will get we will get position plus the output, and we call that add. And the reason that they do is because they try to preserve in long-term memory, just like LSTM, and we can call it residual connection. And once we get add, we will normalize it, which that is why we call norm. It stands for layer normalized. Note that it is not the same as batch normalized. The reason that it's normalized is because it wants to converge to the two parameter faster. And then once we going through this function, the output for that is still the word embedding, but give a different weight for each word. Okay, and once we got the result here, we will repeat that for 12 times so it can learn something that is more complicated. And the reason that we repeat 12 times because we have 12 attention layers, right? Yeah. Okay, and here is the visualization of how each layer and each head will interact between each one and each one. Okay, and if you want to see more about the visualization, you can scan the QR code here at the below, right below. Okay, that's all for how the model burst looks like. It looks simple, right? Um, okay, let me recap again. So first of all, our input here is the below. I feel romance too. Once we point into to our bird model, then what is the return will looks like something like this. It will assign the weight for each word not equally. In this case, you can see that the word I feel low and romance get the highest weight. But note that the probability, the weight of them when we pass together must be 1, just like a probability theory. Okay, next. That's all for the part that how the bird really works. So next, you may wonder how we train the model using our data set. So first of all, here's the analogy for how we train the data. Um, this is a bird in general, but we want it to specialize on reading the text message. So once we input the data set, we'll get something called Commuji bird. Okay, so there are two phases for the training bird here. Pre-training phase and fine-tuning phase. So I will go with. Okay, so our first phase is called pre-training. So the idea here is we just want the model bird trying to familiar what does the text message looks like. So it make it understand the specific feel of this text much better. And the reason that we have to do this phase is because as we know before that the P10 model called BERT base is doesn't really learn the word that maybe that the text message contain. So we have to make it more than just general but rather specific for the text messaging. That's the idea. Okay, so first the way it can learn is that has two things. First one is math language modeling, which the abbreviation is MLM, and next sentence prediction, which abbreviation is NSP. Okay, so uh, let's talk about MLM. So basically, this is not that hard because the input here is just the sentence, our observation. I feel romance too, and then we will randomly match the word. In this case, it matched the word called romance. And here the analogy for that is just like hiding that word. So it will make that model trying to fill the blank. And in this case, the model think that, oh, the word in math, maybe it is the bad because it has the probability to be in bad, which is totally wrong for in this case. So we want the model to learn more better on what does a text message mostly looks like, and then we punish them by giving them the loss so they can doing back propagation and then update the parameter like uh, input embedding and may slightly update the parameter for the BERT model. Okay, and next loss is called next sentence prediction. I have to disclaim this first because most of our observation is consists of a single sentence, so it might not be useful much for updating the parameter. However, I will show you how does work. So suppose like this observation, it has the word I feel romance to my feeling. The first thing that they will do is cut them, and then they will separate them into two objects, and then it will predict that does sentence A is come before sentence B or sentence B is come before sentence A. In my opinion, if I was model, I would think like, my feeling, I feel romance too. I think my feeling should come before I feel romance too. I think that's more makes sense. If I was model, then I will return one. However, if it does not predicting like me, it doesn't say so, then it will return 0. Which is wrong if they doesn't believe in me. So they will get a loss function and they will have to update input embedding. Okay, next one, they feel familiar with the word in the text messaging. Now we want it to classify what is the label for that. What we can do here, we just block the layer called feed-forward neural network. And the number of hidden layer is really depend on you, like the number of hidden layer. But the softmax must have 6 layer here because we have the 6 emoji, right? So what we really want, we expect the softmax return is return the probability of each emoji. So the emoji that will be picked it must have the highest probability. In this case, suppose like the probability of laughing is 0.8, then it will select this laughing emoji. Because the rest will be something like 0.03 and something like that. And if it predicts wrong, then it will send back the loss function and doing some kind of back propagation to update the parameter in the feed-forward neural network. And we have to train over and over again. And that's it for how we train a model. And next, let's see how what is the performance of our Commuji model can make based on the test set. Okay, you can see that the accuracy for each level is pretty good here, and you can evaluate it by using weight F1 score, and the result is really impressive. It's achieved more than 90%. Yeah, hooray. Okay, and here is the example of how our model predicts. So let me read the first observation. What if the keeping murderer is in your house? And it's pretty fear emoji. Wow, that is true, and I believe that most of people really think that uh, they will use fear emoji, right? Because the creepy murderer make the word creepy murderer got attention the most. So the attention weight for creepy and murderer should have the most if our model is very good and our community really does really good at this. And I'm sorry to hear that. I think in this case, I think BERT model will really focus on the word sorry the most, so that's why it's written sad. This is correct, and so on. However, just like a human, they can make a mistake. So So here is, I will show you how the model make a mistake. For the first observation, I think it's too long to read. The second one, I feel very strange today. The true label for that is fear, but it predicts something like surprise, which is, in my opinion, I don't think that is totally wrong, because feeling strange is something that you might be wondering, or something that surprise you. So I really get why the model predict wow emoji, surprising emoji. So this misclassification of this observation really make suggest me to have more than just one emoji classification. So it should not be the classification problem. I think it should be a recommendation of emoji problem, because human many humans have a different perspective of having just the one line emoji. So we better suggest more than just one emoji. That is our first future improvement. We will update the model for that. By the way we can update for that is, since the softmax layer return the probability of each emoji, then we will select the first T line that has the highest probability respectively. Okay, and next observation that I will let you focus on is the last observation. I feel assaulted by all direction. The true label for that is sad, but it's pretty fair. Hmm. In my opinion, I think it really depends on the story, right? I mean, the story before this text message. So it is possible to be both free and sad. It really depends. So what really suggests me for the second future improvement is the data for that should be long enough to know what the really context and what should be the right emoji for that. This yeah, and that is our future improvement from that we got from this classification. Okay, and that's all for how we train the model. And to sum up, the model Commuji BERT do a really good job on predicting the emoji. However, we also learned that this test should not be a really classification, but rather called recommendation, because um, many humans have a different perspective on the right emoji, right? So the way we will do it is we will suggest the first three emoji that has the highest probability, and um, the second one is the data should have longer than before. In this case, my opinion is the data here should look at the previous chat. I mean, like uh, it should look the story before that. What did they text before and something like that, so they can precisely predict the emoji better. And now let's talk about why the BERT model is so special. So first of all, it had a multi-attention head layer slide, and so this means that it can focus on the specific word to it can pick what should be the word that it should be focused at the most. That that is better than focus in a whole sentence, unlike the IN and LSTM. And also, what makes BERT really make it faster is it can perform in parallel when preserving the order of each word. So that is really good. You just find the position encoding for each word by plugging the position index. So this means that each word doesn't depend on each other. They just use their own position index. Unlike the LSTM or IN that they have to wait each word to done first, so they can perform next and next and next. So um, and it can also preserve the long-term memory by using the function add and then normalize it. Okay, that's all uh, for our community, and now we want to special thank to these two guys. For the first one, Hiro Matt of Internet. Sorry if I mispronounce your name. She really provide a really simple visualization for the transformer, even though it's simple, but it's really make me understanding intuitive way. And once I understand it, I can understand the math equation really not that hard because I understand it before by her visualization. So thank you very much. And and I must confess that most of the figure of the image that I show you is from her from she, yeah. So thank you very much. And for the code emporium, once I know the transformer architecture, I really want to focus on how the difference between transformer and BERT. So he really did a good explanation, just like the hero that make me understand in intuitive way. So thank you very much for the review. A big credit